Hello, and thank you for joining us for the SLW Institute webinar, Patenting Artificial Intelligence Inventions for Companies Outside the Software Industry. A recording of the webinar and the slides will be emailed to all registrants. Feel free to enter any questions using the Q&A feature on the Zoom menu. Our speaker today will be Greg Rabin. And with that, I'll turn things over to Greg.
Thanks, Bree. So I'm going to be talking about patenting artificial intelligence for companies outside the software industry. A bit of my background is displayed on the screen. It's also on the SLW website. If you type in Greg Rabin SLW into Google, then you'll be able to see a link to my bio and learn all about my background and interests. And so I'll start with a brief introduction to machine learning. Then I'll talk about machine learning in non-software companies, some key players and trends in the field, how to capture and protect AI intellectual property, and AI stands for artificial intelligence, patentable ML machine learning technologies for non-software companies, and the state of ML and the current patent-eligible subject matter law, and the written description and functional claiming requirements for machine learning inventions. So basically in the last couple of decades, there has been a resurgence of AI. So the general ideas of AI were mostly invented in the 1950s, 1960s, and 1970s in the United States, the former Soviet Union, and in India. But most of the inventions at the time were very theoretical because the computing infrastructure to implement the AI inventions just did not exist. But now that we have powerful computing tools and we have the availability of GPUs that can run multiple processes in parallel, and if you run the same process across multiple different computing machines, then you can benefit even more from parallelism. And we have a lot of data about people, like all of the big tech companies, Google, Facebook, Twitter, are in the business of collecting a bunch of data about their users and using that data in order to make money. And this results in the development of smart algorithms, and also there are a bunch of voice and image sensor technology. Like now, cameras are very cheap, so it's very easy to deploy cameras report, as is being done already in China and might be done in the future in the United States, especially in response to the COVID and people's interest in having a lot of things be touch-free and no contact. So basically, there's an increased need to identify patterns with large volumes of business data, and the large volumes of data are now available for this purpose for the first time in history. And basically, the AI market had an upward trend, at least until the last several months. And this upward trend is, at least based on the stock market, it's expected to continue into the future. And these last few months will probably be a small downward blip in that trend. So basically, there's going to be between 3.5 and 5.8 trillion in value across multiple industries. And there's a lot of government investment in the US. DARPA is investing $2 billion to develop the next wave of AI technology. And China has a stated goal to create $1 trillion AI industry by the year 2030. So now I'll talk about machine learning and non-software companies. So we'll start by defining machine learning. And here is a Dilbert cartoon, which pretty much defines it. Basically, the boss's computer determines that he might be dumb enough to enjoy extreme sports, and he's offered to buy a ticket to base jump from the International Space Station. And he determines that the internet is trying to kill him, and Dilbert tells him that this is called machine learning. So on a more serious note, machine learning basically gives computers the ability to learn without being programmed. Traditionally, in computer science, a programmer would write some code and the computer would execute that code line by line, and basically the programmer tells the computer exactly, then executes those steps in order to do whatever needs to be done. For example, if you wanted to determine whether an image includes at least 10 green pixels, then you would basically open an image, count green pixels, and if that number is greater than 10, output true, and if it's less than 10, then output false. And this is a simple linear equation. Machine learning, on the other hand, for example, you can identify whether an image includes a cat or a dog. And you don't have to necessarily be able to specify the instructions like I did with the 10 green pixels example in order to determine whether there's cat or dog. Instead, you can show the computer a bunch of images that are cats and are not cats, and then the computer would teach itself to identify whether an image includes a cat. So some use cases for machine learning include basically the detection of network intruders, optical character recognition, and a computer field with many subfields and many uses. Some uses include computer vision, as I mentioned previously, natural language processing, and speech processing. And the machine learning algorithm include deep learning, decision trees, Bayesian algorithms, artificial neural networks, decision trees, and clustering algorithms. And each one of these algorithms is worthy of its own 1-hour talk. So I won't go into too much detail here unless you have specific questions, which you may enter into the Q&A. So is machine learning, some consideration you might have, or is machine learning being used to solve a specific commercial need in your industry? Like for example, is machine learning being used to go through many different chemicals in order to action that's good for a specific task? And as machine learning models are becoming smarter, they can solve more and more problems. So right now there are simple chatbots, a lot of websites, for example, banking or airline websites have simple chatbots that get a user to an appropriate person if there is a complicated question that the simple chatbot cannot handle. But as these chatbots become more advanced, they could actually have actual conversations with people and generate ideas for solving a person's problems. For example, a chatbot could operate more similarly to a human in terms of basically handling a credit card transaction dispute, as opposed to just asking questions about like, what do you want to do? And then identifying from the user answer if they have a transaction dispute, and then sending it to a human who would get the information and identify the details of the dispute and process the dispute with the bank and the merchant. So also think about how you would feel if a competitor applied for a patent on technology similar to the one that you're developing, because different companies operate in parallel and often try to problems. And another question is, how valuable is the technology to your company? Is this technology going to cover a large proportion of your company's revenue, or is it just a small technology that's not really a big deal in the grand scheme of things? So also, machine learning could be used to supplement the use of human researchers or to guide researcher, saving them time. For example, I recently read for COVID-19, some researchers were using machine learning algorithms to go through a huge repository of chemicals and existing drugs to determine which drugs could bind with the COVID-19 virus's proteins to prevent the activation of the virus. And so in the future, I think most companies will have to at least consider machine learning as part of their strategy. It might be okay not to use machine learning in some cases. For example, at the end of the day, maybe a human researcher needs to go through any final recommendations and determine whether the recommendations are suitable enough to conduct a detailed study, or if the recommendation should be just thrown out. But at least it should be considered to consider at least using machine learning for the beginning stages of any research. So why should non-software companies care about machine learning? And by non-software company, I mean any company whose primary business is not in the computer software space. So machine learning is a fast-growing field, as we discussed, and many forecasters expect this growth to continue to accelerate in the future. And machine learning is being used more and more in traditionally non-software fields. In the past, machine learning was used only by Google and Facebook to mine data and identify which advertisements to show to their users, but now it's being used by non-software companies in more and more spaces. For example, marketing and sales, manufacturing, supply chain planning, medicinal chemistry, and computational chemistry, as I alluded to earlier with the COVID-19 example. So another example of a company that's working in the machine learning space and is not a traditional software company is Atomwise. They are a biochemical discovery startup in San Francisco, and they deployed a deep learning machine called AtomNet to tackle key real-world issues in improving pesticides. And basically, the deep learning allowed them to simulate millions of compounds and identify the ones that are going to target pests without causing toxicity in humans and other friendly species in the best way. And this has allowed the company to produce less harmful products faster than competitors, which rely on scientists for all of the steps from A to Z. And Atomwise instead only has a scientist look at the results outputted by the machine learning model at the very end, and this allows them to iterate through the different compounds much faster. And so one benefit of machine learning is faster iteration, and samples can be generated and tested much more quickly by machines than by humans. And in one example, like Dilbert creator Scott Adams, in his writing admits he tried many different cartoons before he developed Dilbert and became successful through it. And the iteration process took Adams many years because he had to create a cartoon, draw it by hand, and then send it to a newspaper, have the newspaper publish it for a few days and see how much interest the cartoon generated, and then move on to the next one. But right now, it could be imagined that an artificial intelligence engine could create a bunch of cartoons and post them to Twitter or Facebook in real time, and then see how much interest is generated in those cartoons and very quickly iterate and improve the cartoons based on the feedback being delivered much more quickly and the new samples being developed much more quickly also. And there could be some kind of artificial intelligence processing of the comments on the cartoons also, in order to basically determine like which aspects of the cartoon are more interesting and which aspects should be removed. So the iteration process, even in creating some art like a cartoon, could operate much more quickly. And I believe that we'll see some computer generated cartoons and similar art forms within the next decade, almost definitely. And in the technology space, similarly, the faster iteration allowed Atomwise to develop pesticides much more quickly than its competitors who use traditional schemes. So now I'll talk about some key players in the artificial intelligence and machine learning space. So if you look at the growth of patent protection for artificial intelligence and machine learning within the last 20 years, you see a clear upward trend up through 2018, and then 2019 is a bit lower because at the time this data set was generated, all of the 2019 patents might have not been calculated yet, but in the long run, I expect this upward trend to continue. And if you look at keyword clustering, then basically most of the artificial intelligence patents are related to machine learning, voice recognition, image data, user interfaces, speech recognition, and neural networks. So now I'll talk about how to capture and protect artificial intelligence intellectual property. So basically, there are many different machine learning related inventions that could be looked at. You can look at some rules that the machine learning engine is applying. You can look at the training data sets and if there are different between your invention and the previously existing technologies. Is there hardware software platform independence, or are you using a specific hardware and software platform? Especially if you can connect the invention to hardware, that would be very helpful to patenting the invention. And you of course want to have sufficiently enabling descriptions so that an engineer working at a competitor could read the patent application and basically build the same system. And you want to disclose the best mode known to the inventors to implement the invention. And you, of course, always want to consider, especially for machine learning inventions that are being implemented on the back end and not visible to the end user, whether a trade secret would be a better way to protect the invention, because in some cases, even if you get a patent issued on a given invention, it might not be very valuable if someone can infringe it without getting caught and getting a penalty as a result of being caught. And you want to consider whether you're using any open source components or components from third parties, because ideally you want your patent to read on your invention and not your competitors or third-party inventions. So US Patent Inventorship currently awards patents to individuals and not computers. And basically a human has to be involved in the conception of the invention, and the reduction to practice can be done by a machine. So conception could be thought of as basically coming up with the general concept of the invention and forming in the mind of the inventor a definite and permanent idea of the invention. So basically, I liken to like a professor comes up with a high level idea and then discloses it to a graduate student, and the graduate student uses techniques known in the field in order to bring the idea to life. And then the professor has done the conception part, and the graduate student does the reduction to practice. So if the role of the graduate student is taken over by a machine, then basically the professor can still be issued a patent on the invention. But if the role of the professor is taken over by the machine and there is no human involvement in the invention, or the human involvement is simply at the level of bringing the invention thought of by the machine to life at the level of the graduate student, then in this case, it's unclear whether current US patent law would allow for a patent to be issued. Definitely, you can't issue a patent to a machine. The inventor has to be a human according to the current law, and the law would have to change in order for a patent to be issued to a machine. So at the current point, like a human has to be somehow involved in the conception of the invention in order for a patent to be issued. And if there are joint inventors, then joint inventors have to be aware of each other's work. So a first inventor could work on an invention, and then a second inventor could work on it. And as long as the second inventor is thinking of some of the concepts of the invention and not just applying routine knowledge or skill in the relevant field, then the two inventors are both joint inventors. But if the second inventor is fulfilling the role of the graduate student in the example I described earlier, then the professor alone would be the inventor and not the graduate student. But if the graduate student added some new concepts that another similar graduate student would not necessarily come up with, then the graduate student would also be an inventor. So now we'll talk about patentable machine learning inventions for non-software companies. So basically, there are two different avenues for patenting machine learning inventions for non-software companies. The first one is new approaches using machine learning technology to solving problems in the company's line of business. For example, if you're using machine learning technology to identify chemicals or atoms or molecules that could be useful for pesticides, then that would be in number one. And number two is new machine learning technologies themselves. If you develop a new neural network to identify chemicals that would be useful for placing in pesticides. And of course, there could be a lot of overlap between number one and number two. For example, you could have a new approach to machine learning technology that also involves a new neural network, because the problem you're solving is different from one that neural networks or other machine learning technologies were used to solve previously. So for new approaches to problem solving using machine learning, the grandfather of these cases is Diamond v. Diehr, which the Supreme Court decided in 1981. And the issue was the validity of a US patent issued to James Diehr in Troy, Michigan, which was directed to direct digital control of rubber molding processes. So basically, Diehr invented a rubber curing process for use in tire manufacture. And the novel aspect was that there was a computer that was controlling the rubber curing process and determining when to adjust the temperature and when to stop the curing process based on the Arrhenius equations, which were known prior art. And the Supreme Court held that if you're controlling a physical process by running a computer program, then that could be patentable, and the novelty could lie either in the computer program or in the physical process that is being controlled. And basically, you can see figure 1, which basically explains like the invention in the Diehr patent. Basically, the Arrhenius reaction constants are stored in a data storage unit and provided to a computer, and the computer monitors a mold that is being cured manually, and there's an input signal that's sent to start, and then timing sent to the computer, and the computer measures the mold temperature every 10 seconds, and the computer compares the calculated cure time with the elapsed time every second, and the mold is opened when the calculated cure time equals or elapses the cure time, and the computer controls the temperature using a control algorithm, as you can see in figure 1. So this patent was filed in 1975 and issued in 1982. It's not machine learning, it's a basic 1970s computer that is pre-programmed with instructions and does not have the processing or memory capabilities to run machine learning. But this computer gathers data from data storage and the environment, i.e. the mold temperature, and makes decisions based on this data using pre-programmed rules. So the Diehr patent is far from modern machine learning. As you can see, it was implemented on a simple 1970s computer with a floppy disk drive, as shown in this picture. And if you were to modernize the invention, basically the Diehr patent is gathering data from data storage and the environment and making decisions based on the data using pre-programmed rules. So in a modern embodiment, you can replace the pre-programmed rules with a trained neural network and a description of the training process, and ideally some kind of novelties in the structure of the neural network. And you can have a machine learning invention that's patentable under the rules expressed by the Supreme Court in Diehr, which is an old and well-settled case. So this is the type of case that many software companies wish they had to support their patents with. But as a non-software company, if you develop the technology, you might be able to rely on the Diehr case to ensure that the technology is patentable, and that will allow you to overcome any Section 101 or Alice and Mayo based rejections. So machine learning technologies that are likely patentable under Diehr. So basically using a trained neural network to control the fabrication of any chemical, for example, a rubber, a glass, or a detergent, or using a trained neural network to control development of a biological or biomedical compound, such as a drug, a vaccine, an artificial limb, an artificial organ, a lab-grown meat, and the like. And these are basically some of the easiest 101 hurdles to overcome. And software companies wish it were this easy for them. And it's just like the difference between traffic in Toronto, as shown at the top of this diagram, and traffic in Silicon Valley, as shown at the bottom of this slide. So some modern examples of the Diamond v. Diehr approach are basically a US patent I found at number 8478535, if you want to look it up on your own, which was issued to Nebojsa Jojic of Redmond, Washington, originally assigned to Microsoft Corporation. This was filed in 2005 and issued in 2013. And this patent application utilizes machine learning algorithm to facilitate assembly of AIDS vaccine cocktails. And basically, they're using machine learning techniques to generate vaccine cocktails for species of pathogens that evolve quickly under immune pressure of the host. And the general idea is shown in figure 3 of the patent application, which basically has some patches being provided to an input component, and then a modeling engine accesses a machine learning component and an intelligence component in order to generate an epitome. And so basically, this application uses the ideas in Diamond v. Diehr to basically reach a technology that controls some machine outside of the computer in order, and receives input signals from the machine outside the computer in order to be clearly patentable under the Diehr precedent. And the next one I'll talk about is, of course, new machine learning technologies, which could be developed by companies outside the software industry. And the reason new machine learning technologies might be developed is that very different problems may require very different machine learning technologies. So typically, when faced with new machine learning problems, software companies don't attempt to reinvent the wheel. Instead, they attempt to recycle pre-existing technologies to solve them. For example, we have software now that is pretty good at facial recognition. So for example, my iPhone can recognize my face when I try to unlock it. And if I try to unlock it, then it lets me unlock it. But if my 19-month-old son tries to unlock my iPhone, then he can't do it because his face looks different from mine. So if we have a new problem, for example, recognizing the faces of cats, then cat faces are not that different from human faces and have many of the same textures and features. So it is possible to retrain a human facial recognition model to recognize cat faces. And after running that training many times, then you'll have a model that's pretty good at recognizing cat faces, so that it could tell the difference between your cat and your neighbor's cat. But this might not always work, because like changing from human to cat facial recognition could be a fairly minor change that is doable. But if you're going from human facial recognition to recognizing a complex chemical, that might be more difficult, and you might need to significantly change the structure of the neural network rather than just simply retrain a previously existing neural network. And in this case, you might have a new feature vector or new data studied by the neural network to draw conclusions, and you'll most likely need a new training data set or a completely new neural network structure with different layers and different math being done at each layer in order to get from the input to the output. And those things could, of course, be patentable independently of the Diehr precedent. And in this case, you're looking at advances in the field of computer science itself, or improvements to the operation of the computer itself, as the Federal Circuit Court wrote in the EnFish v. Microsoft case, rather than just simply using a computer to solve a problem in another field, as in the Diamond v. Diehr case. And here you have a new neural network itself versus a neural network that was invented by someone else that's being used to control a process of curing rubber. So now let's turn to machine learning and current patent eligible subject matter. So basically under 35 USC 101, to be eligible for a patent, the subject matter of a claim must be directed to a process, machine, manufacture, or composition of matter. And there are judicial exceptions to patent eligibility for abstract ideas, like, for example, if you have a purely mathematical algorithm, then that would not be patentable, or something that is a law of nature. For example, if you tried to patent the Arrhenius equations without tying them to a computer that's controlling the process of curing rubber, then the Arrhenius equations by themselves would not be patentable. And any other natural phenomena, for example, you can't patent the quadratic formula, even if you invent it yourself, because that is just a natural phenomenon that exists in nature and is not tied to a problem and solution in an engineering sense. So the ALICE test was developed by the Supreme Court in the ALICE v. CLS Bank case from 2014, which basically looks at, is the claim tied to a process, machine, manufacture, composition of matter, and if it is not, then it's not patent eligible. And if it is, then we look at whether the claim is directed to a law of nature, a natural phenomenon, or an abstract idea. If it's not directed to an abstract idea, then it's patentable. But if it is directed to an abstract idea, then the court looked at whether the claim recites additional elements that amount to significantly more than the judicial exception. And if there are additional elements that amount significantly more, then the technology is patentable. And if not, then it is not patent eligible under 35 USC 101 and the ALICE precedent. So you might want to draft machine learning claims to recite a specific improvement in computer technology based on the EnFish v. Microsoft Federal Circuit case, which I discussed earlier. And in EnFish, the court reviewed claims that recite a self-referential table, which was a specific type of data structure designed to improve the way a computer stores and retrieves data in memory. And the claim recited a means for configuring, and the specification described a four-step algorithm for configuring a self-referential table. And the court said that these claims were directed to an improvement in the functioning of the computer, and therefore they were patent eligible. And in Thales Visionix v. United States, this was related to another patent that disclosed an inertial tracking system for tracking the motion of an object relative to a moving reference frame. And there were sensors that calculate the position, orientation, and velocity of the object in 3D space. And this patent application basically used inertial sensors in a non-conventional manner to reduce errors in measuring the relative position and orientation of the object. And basically, because this was an application or use of data, not just the generation of data, the Federal Circuit found that this technology was patent eligible. So basically, you want to show in your disclosure forms that you or in your patent applications when they're drafted, you want to show that you're covering applications or use of data, not just the generation of data, and doing something more than simply a computer receiving an input, doing some math on the input, and generating an output. So if you look at claim 1, it basically, I'll let you read it yourself, but the red underlined parts show show the key features that I believe the court relied upon in reaching its conclusion of patent eligibility. And the next case I want to talk about is McCrow, and in this case covered a patent claiming a method for automating parts of a pre-existing 3D animation and automating the facial expressions of animated characters through rule sets. And this patent recited a combined order of specific rules that rendered information in a specific format and was patent eligible. So here, once again, the court looked at how the data was formatted and the specific rules that were being used. And basically similar to the EnFish case, the court found that this claim was specific enough to take it away from the space of a computer doing math and arriving at an output. And as you can see, the claim included a lot of implementation details that go beyond like receiving an input, doing math on the input, and providing an output. I'll let you read the claim yourself, and basically the red underlined part is the part that I believe was most pertinent to the patentability analysis by the Federal Circuit. So the next case I'll talk about is Vehicle Intelligence and Safety v. Mercedes-Benz. So this was a patent that had a claim directed to method and systems that screen equipment operators use the screen equipment operators for impairment and test those operators and control the equipment themselves if impairment is detected. So basically, if a drunk person tries to drive a car, then basically the computer would determine that the person is drunk and unable to safely drive, and the computer would control the car itself instead of allowing the person to drive. And this claim said that there's an expert system that detects impairment and controls the operation of the vehicle. And basically the court said that this patent was drawn to a patent ineligible concept because it was directed to an abstract idea of testing operators for any kind of physical or mental impairment. So basically the claim was too broad and too vague, and some more specificity of what exactly the machine is doing and how it is, what inputs it's receiving and how it's processing those inputs to determine that the operator is impaired, and then how the machine is controlling the vehicle would have been beneficial to allow this patent to be patent eligible. And you can look at the claim, and basically the court didn't like that you're claiming an expert system, but you're not disclosing within the claim what exactly the expert system is and how it works and how it's constructed. So it's sort of like more of a 112-ish rejection, because the expert and a skilled person would not understand based on this claim alone. Maybe they would if they read the specification. I'd have to look at that offline, but basically the expert system alone like covers a bunch of things that the inventors did not invent, and the court was hoping to have something that's more focused on the exact invention rather than claiming that, oh, the invention is an expert system. Written description and functional claiming in the machine learning context. So 35 USC 112 talks about written description requirement and means plus function claiming. And basically, the specification needs to contain a written description of the invention so that a skilled person in the relevant field could read the application and understand how to build the technology. And generally, by skilled person in the field, they mean like an engineer at a competitor company who necessarily worked on this invention before, could read the patent application and understand it and build a similar system to the one covered by the patent application. and some say a means for doing X without reciting a specific structure, and that claim would correspond to any means disclosed for doing the thing that's covered by the claim, disclosed specification, but not other means. So these means plus function claims could be useful in some cases, but in some cases you want to avoid them because typically when the invention is implemented by an infringing party, they might do some things that are different from what's disclosed in your specification. And in that case, you want to still be able to cover what they're doing, which is why typically we include method, system, and computer-readable medium claims, and we try not to get them to be covered by the means plus function claiming requirements. But of course, in some cases, means plus function might be a useful way of claiming certain technologies. And before the Williamson case, basically, it was believed that a claim had to explicitly recite means for to invoke the 112F, 112 paragraph 6. And a claim that did not include the word means instruction, and the presumption was that in the absence of the term means, it was generally not a means plus function claim, and this was a strong presumption that was difficult to overcome. And the only way the statutory construction not be applied is if the limitation was devoid of anything that could be construed as a structure. And after Williamson, the strong presumption was removed, and basically the standard is now whether the words could be understood by a skilled person to be sufficiently definite as meaning the name, have sufficiently definite meaning so that they would cover a given structure. So basically, courts have held that some nonce words invoke the section 112F or 112 paragraph 6, and some words don't. So basically, if you say circuitry, processor, computing unit, detent mechanism, digital detector, reciprocating member, connector, assembly, or hanger member, then these words do not invoke 112F paragraph 6, but words like module, unit, device, mechanism, element, system, component, member, apparatus, or machine are going to invoke 112F, and you generally want to avoid using these words in your claims unless you are specifically targeting a 112F interpretation, in which case you might as well just say means for. And if you don't want a 112F interpretation, then ideally you use circuitry or processor or computing unit or some other word that is not a nonce word that has some kind of meaning. Typically, I like to use the word engine, and then I define in my specification that an engine could be implemented in software, hardware, or a combination of software and hardware. And at least at the level of examination at the patent office, this has allowed most of my claims not to get the 112F interpretation. So if you employ means plus function claiming, then the specification needs to include an adequate disclosure showing what is meant by the language. And basically you need to make sure that if you say means for X, then the specification explains how the X would be built and what structures would be used to achieve X. And if a corresponding structure is disclosed in specification, it should be disclosed in a way that a skilled person in the art could basically read the specification and understand what structure will perform the recited function. So you need to show that basically what structures you're using, like what data structures you're using, what software, what hardware, like how exactly would this be done in order to satisfy the 112F requirements. And so you need disclosure of a structure that corresponds to the claim function, and disclosure of a general purpose computer is not enough when the element must be implemented on a special purpose computer. So if you have something that a general purpose computer can do, such as like reading a value from memory and displaying the value on the screen, then that's something a general purpose computer can do. So you can disclose a general purpose computer to do that. But if you have an algorithm that is running a complex multi-threaded process and it's accessing a huge amount of memory, then you need to disclose your high-end back-end server that is able to do these calculations if you want to use means plus function claiming. And basically, in court, an expert declaration of person ordinary, that a person of ordinary skill in the art would know what was needed is not enough. You need to actually disclose it in the patent application, and just having an illustration of the function being performed is not a substitute for just actually disclosing the algorithm that is being used and the software and hardware on which the algorithm is being run. And basically, a programmed computer functions require computer programs and algorithms to perform the functions, and specialized functions need to have an algorithm that's disclosed. For example, an event detection system that communicates network event information. A skilled person would not know how to do this without disclosing an algorithm. But any non-specialized functions would be something that you can just disclose a general purpose computer, and a skilled person understand how to do that. For example, if you're saying means for storing data, then any college graduate in computer science would know what means for storing data are and how that would be implemented. So you don't need to disclose anything more than a typical Windows computer to do that. And you want to avoid indefiniteness when claiming machine learning, and especially in the machine learning context when a lot of the calculations are done in the black box, indefiniteness could be a big issue. And in Gradient v. Skype, basically Skype successfully argued that the system claims, i.e. claim 27 is dependent claims, are invalid under section 112F because the patent did not disclose adequate structure corresponding to the claimed function. So if you look at the claim over here, basically it claims a designation system that designates mobile agents as controlling mobile agents. It designates another one of the mobile agents hosted on another one of the nodes as the controlling mobile agent. And basically, there's no disclosure in the specification of what is this designation system other than possibly a general purpose computer. And and in claims 28, 29, and 32, basically claim 28 says what the designation system does, and it determines something. Claim 32 says that the designation agent determines something, and claim 29 says that the designation system uses a voting and artificial intelligence algorithm, but there's no disclosure of what exactly is the artificial intelligence algorithm. So this claim was invalid because the artificial intelligence algorithm itself was not disclosed in the specification, and the drafting attorney assumed that a skilled person would know what an artificial intelligence algorithm is and how it would be programmed, but that was not the assumption that the court agreed would be valid. So as a best practice, if you're disclosing an artificial intelligence or claiming an artificial intelligence algorithm, then you should disclose at least one artificial intelligence algorithm that would do the task, and disclose the hardware on which the artificial intelligence algorithm is running and the software that's being used to run it. So now I'll talk about computer-readable medium claims. A computer-readable medium claim basically says a non-transitory machine-readable medium that stores instructions that, when executed by a computer, cause the computer to perform operations comprising and then the operations of an algorithm. And it's a hybrid of an apparatus and method claim, having properties of both, because you're not claiming the processor, you're just claiming the memory unit, because you're saying computer-readable medium storing instructions that cause the computer-readable medium to perform a method. And computer-readable medium claims are still viable options valid today, and these are arguably the most valuable claims because the method claim requires performing the method to infringe it, and the system claim requires having a computer that includes a processor and stores a memory unit, whereas a computer-readable medium is just the disk on which the algorithm lives. So if you have a company that is selling CDs that perform your method at Staples, then that company would be infringing. Or if they're providing the if they're storing the algorithm in the App Store for download to an Apple or an Android device, then they would also be infringing because they're storing in memory some instructions that cause the memory to perform a set of operations, and that would infringe the computer-readable medium claim, but not necessarily the system or the method claim until the method is executed or it's stored, or the method or the algorithm is stored on the end user device. And the USPTO explicitly endorsed computer-readable medium claims as patent eligible by listing them in their post-Alice Section 101 guidance and patent eligible subject matter. And this is an example of a computer-readable medium claim. As you can see, it recites a non-transitory computer-readable storage medium, including computer executable instructions, which when loaded onto a computing system, execute a routine comprising it by the computer in order to achieve a certain result. And some machine learning technologies you probably want to avoid patenting. For example, if you have a purely mathematical algorithm or a non-technological business algorithm that does not impact anything outside the computer. As I mentioned previously, the Patent Office is currently looking down on an algorithm that basically receives an input, does some math on the input, and provides an output. Like even if the math itself, the Patent Office generally does not like this type of claims, but of course there are exceptions, and we could look into that privately. If you want to give me a call or send me an email, we can discuss your specific case offline. And some examples of technologies that the Patent Office doesn't like are techniques for hedging investment risks, computations done inside a computer that do not have a real world impact and are not tied to the functionality of the computer. For example, a GPU in memory structures or data structures. If you have a technique for hedging investment risks that's tied to a GPU and that's implemented on a GPU using specialized GPU hardware, then that might be patentable. But if you have just a mathematical algorithm for hedging investment risk, then the Patent Office is unlikely to like that. And if you have these types of technologies that are not patentable, you might want to consider either a trade secret or a defensive publication to prevent your competitors from getting patents if the law changes. And so for application drafting strategies, you might want to recite specific elements and or ordered combination and focus on technological aspects, and avoid technology that reads on mental thoughts or sounds like a human is doing it. For example, determining a crash occurrence, it's okay and it might be acceptable in some cases, but the Patent Office, when the patent examiner reads this claim, like they hear determining a crash occurrence and they think that this is something that a human is doing in her head and they don't like it. But if you have something that says analyzing sensor data to determine if received sensor value exceeds a deceleration threshold, which is essentially the same thing as determining a crash occurrence, but this seems like a computer is doing it because the computer is receiving the sensor data and analyzing it to determine if a deceleration threshold has been met. And you want to, in your claims, recite more than conventional computer processing steps or functions. As I mentioned previously, the Patent Office does not like purely conventional steps where a computer receives an input and generates an output and does some math. They want to see some kind of data structures or some kind of novel computing elements that improve the functioning of the computer itself or control a machine outside of the computer. And you want to include some implementation details in your claims that would clearly move the patent application from the theoretical space to the practical implementation space. And if the novelty is in the algorithm itself, then means plus function claims might be valuable. And If not, then you might want to focus on the computer-readable medium method and system claims. And you should always consider computer-readable medium claims. I try to include them in most of my patent applications. And you might want to consider multiple different types of claims. So I typically include computer-readable medium claims, method claims, and system claims. Functional claims I use less frequently, but they could be useful in some cases. And the specification should be focused on the technical aspects of the invention, and it should identify the problem in the art and explain what is the invention specifically improving over the prior art. And of course, don't characterize any claim elements as conventional, routine, or commercially available. And overly abstract language should not be used to describe the invention. And if some individual steps are well known, then you should emphasize how the combination of the steps is far from routine and conventional, and somehow show that basically the steps alone might be known, but using these steps in combination might not be well known. For example, using a neural network to recognize faces is well known, but using the same neural network in a completely different context with completely different inputs and outputs would not be as well known. And so thanks a lot for listening to my presentation. I'll take a look at the Q&A at this time. I see there are 3 questions, so I'll take a look at those. Let me see the Q&A. So what do you mean by computer vision? Does it pertain to the quality of displays in the computer? Does it pertain to accessibility or readability? So by computer vision, basically I mean a camera that serves as an eye. So for example, a computer sees through a camera a certain input and then processes that input similarly to how a human would process visual input. For example, a display board in a store could have a camera that observes a human that interacts with the display board, and then when the human moves their arm, then some items on the display board might be moved. And the display board could be separated from the human by a glass, so the human isn't touching the display board. Instead, the human is moving her hand, and when she moves her hand, the display board moves. Or for example, in China, when people walk into an airport, they can walk up to a screen and the screen will automatically recognize their face and say, "Hi, Jack, you are going on United Airlines flight number 123 to San Francisco, and your flight is at gate D12, and to get to gate D12, turn right here and then turn left on the second hallway." And like that would be a computer vision application. So the next question I see is, for a patent application on the use of a machine learning system to solve a problem, what are the considerations for claiming a trained machine learning system that solves the problem, but preferably not including the training itself in the claim? Basically, you want to have some novelty in the solution. So what exactly are you trying to claim? Like, where is the novelty? The novelty could be in the training. The novelty could be in the structure of the neural network. The novelty could be in the novelty could be in the format of the input or the output. The novelty could be in the features that are considered by the machine learning system. So basically, you want to look at what exactly is, where exactly is the novelty, and focus the claims on that. And of course, you want to keep in mind detectability of infringement. For example, if you're looking at an input and output, then that is a lot more useful than a technology that looks at back-end processing. Does the current technology support the position that machine learning systems may teach themselves unassisted by humans? And if so, the machine learning systems may be readily applied, much like general purpose computers, to solving problems presented to the machine learning system. will the answer to this question change as machine learning technology advances? So machines may, in the current state of the art, my understanding is that generally a human would present a problem to a computer, and the human would use a neural network to solve that problem. But recently, like, there was an article about a machine learning system that itself recognized the problem and developed a solution to it unassisted by humans. And this invention, the European and US patent offices decided it was not patent eligible because there was no human inventor. And in this case, yeah, so in the future, definitely there will be more and more general purpose machine learning algorithms that could identify problems and present solutions themselves that are unaided by humans. And whether these technologies are patentable and whether they should be patentable is a current question that's being debated. And in order for them to be clearly patentable, then the law would have to change to prevent a person from being the inventor. But most technologies right now, I believe we could somehow associate a person with the inventorship and somehow argue that a person participated in the conception of the problem or the conception of the solution, and then that person would be the inventor. And do you have any examples of claims that you've written covering different AI methods? Not off the top of my head, I'd have to also find something that has been published. So that question, you can email me and we can discuss that offline, because it will require me to go back and look at different claims that I or other people have written in order to find the different types of claims other than the ones that were shown in the slides. Are apps patent eligible? So depends on what features of the app you're claiming. If you have a complex gaming app that's using the CPU and GPU in novel and non-obvious ways, then that type of app might be patent eligible. And if you have a simple app that receives an input, does some math, and pops out an output, then probably not, based on the discussion of mathematical patents. So basically, you'd want to look at what are the inventive features of the app and then determine whether the app is eligible based on the inventive features, and maybe write the claim in a way that would cover the inventive features without necessarily tying them to the full app, so that if the same feature is used in a different context, then your patent would still cover that. Is it reasonable to patent methods of generating a data set? Are there any strategies to check the infringement of other companies? Because it is a black box, it can be hard to detect infringement. So methods of generating a data set, like the same considerations that I mentioned in this discussion, would apply. Basically, is there a novelty? Is it non-obvious? And does it go beyond a computer doing some math? Like, is the computer controlling a machine outside the computer, or is it generating data structures or novel ways of storing data? And in terms of checking the infringement of other companies, you would need to first allege some threshold of potential infringement in order to go to discovery. And then once you go to discovery, then you can check the infringement, look at the algorithm in more detail, but generally you're limited to looking at the publicly available inputs and outputs for at least the initial threshold in order to get to the discovery stage. And I would recommend that you speak to someone who's familiar with patent litigation to determine the strategies for checking infringement of other companies. And I believe I've answered all of the questions, so I'll turn it over to Michelle or Bree for the closing comments.
Thank you, Greg, and thank you again for joining us, everyone. Our next webinar is coming up on June 11th, when we have the next episode of the Patent Analytics webinar series. So if you can, we would love to see you back for that. Thanks again and have a good afternoon.